Hello, hello. I'd like to provide a little summary of our latest paper that just came out end of last week. It was released on Friday, and this is about MERAPI Volcano. And MERAPI Volcano is one of the big and dangerous volcanoes in central Java, and it sits very close to the major metropolitan area of Yogyakarta. And this, of course, is a recipe for trouble. And indeed, MERAPI has caused a lot of casualties over the last few hundred years. And there's a lot of effort trying to reduce the impact the volcano has on the life of people there. But, well, volcanoes have good and bad sides. So there's also a lot of livelihoods that are created by the volcano. But one of the big problems the volcano poses is that sometimes it's not always clear when exactly eruptions, explosions, and dome collapses happen. So let me kind of bring you to a few of my visuals that I have prepared now. So here, share screen function. So this is MERAPI, and in the background there's Merbabu. It's an older volcano, and we're looking from south to north here. And old MERAPI is here. There was likely a larger collapse that has occurred, and in that collapse scar we have a new MERAPI growing. And this is the dome area, the summit dome, and this is where lava is extruded. And these domes, it's the best analogy I heard is that it's a bit like toothpaste being squeezed out, and at some point this material then cools, crumbles, and actually it collapses. But it's not always clear when and how these collapses are supposed to occur, and sometimes they happen out of the blue. There's not a lot of precursor warning signals, and that's a key problem. And once they occur, there is material being shed down here, causing these pyroclastic flows. And there is mining, sand mining here in these valleys, and there's villages a little further down. And it would be good to have a better understanding of how these things work. So we have tried to understand this a little better in this paper here. The paper was led by Herlan Darmawan, who is a lecturer now at Gajah Mada University in Yogyakarta. He was a PhD student of GFZ Potsdam, supervised by Thomas Walter, and myself as a second supervisor. So this is these two people here. Francis Deegan here from Uppsala has helped, and Harry Geiger, who was a PhD student here in Uppsala at the time. Mike Heap from Strasbourg was involved, measuring a lot of the kind of mechanical strength aspects of the rocks. Nadira Serafin, she was a master's student here. She helped during field work and also partly during the lab work afterwards. And Chris Harris did the oxygen isotopes. Hani Komita from the observatory, and Daniel Müller, another PhD student at Potsdam, who helped with the remote sensing, and Hannig was helping with the gas chemistry and things, the fluid chemistry on MERAPI. So all of these people have contributed to the article, and we're very happy that it's out now. And we've been working on this for quite a while because it has a lot of drone images that go back up to about something like 10 years. So there's a lot of information that has gone into this. So, I mean, you can read the details, and I will put a link there in the box below. But what this is all about is that we have MERAPI volcano, and there's this southwestern instability zone, and this is causing problems. It's collapsing a lot. And here we have a camera system that looks at this, and this is the angle. So we can see this material being unstable, and it's hot, and it breaks off. And this is an issue. Here's a thermal image, and it shows that there's a heat anomaly in there. So this is warm material that is breaking off, and it does so in a rather irregular fashion. At least it's very hard for us to understand why it's breaking off there, and when it will break off. So we tried to kind of get a better sense for this, and here's some drone images of the crater area. And you see there's yellowish sulfurous material. That's alteration. This is where fluids and gases come out. And the alteration here is marked in yellow here on the little sketch map. And we have taken samples as well. And we tried to locate the fumarole sources. And the samples we have taken are the green stars here. They're actually in the 1902 lava dome, so they are somewhat older, but they are partly outside the alteration zone and partly within the yellowish sulfurous alteration zone. So we looked at samples that are from fairly fresh, ranging all the way to really intensely altered so that they crumble in your hands. And we were trying to then understand what the behavior of the dome would be like if we have more of this material and more of that material. So we looked at the mechanical strength of these rocks and putting this together here, the drone images, this is from 2015 and here from 2017. And here's a vent. And this is in the dome area, in the crater area. And what we see here from 2015 to 2017 is that we get this horseshoe-shaped zone here that has fumarole degassing. And what we have here is that alteration is kind of creeping up to this as well. I can make this a little larger, I think. So here we are. So here we have this horseshoe-shaped area forming, and this is a color analysis of the drone images, and it's allowing us to see where the alteration is particularly strong just by understanding the different colors. And here in the original kind of image, we see the color changes, and the color analysis helps us to make this yet more clear. So, for example, we can now get a sense that something was happening there. There was gas being expelled and alteration of the rock. And if we zoom in, this is the 2015 and the 2017 ones, here you can see that this kind of forming fracture area here that is being exploited by steam and gas. And this is causing the rocks to be intensely altered. And this is expressed as sulfur deposits at the surface. So this gives us a good idea of what's actually going on in that area, and that is that there's a fracture system, and the rocks around this fracture system are actually weakened by alteration. So how strong would that be? Well, we then continued to investigate the rocks that we have sampled, and it's not exactly from this fracture zone, I must stress this, but it's from a similar fracture zone from an older part of the dome complex, the 1902 area, lavas and dome complex. And what we find there is that if we go from fairly fresh rocks to fairly altered rocks, we see dramatic mineralogical changes. We go from a very regular magmatic assemblage of feldspar, in this case andesine, which is a plagioclase feldspar, and some CPX, clinopyroxene, and a bit of opaques like magnetite, to an assemblage that is actually marked by a lot of alteration material, gypsum, sodium alunite, and there's a bit of CPX left, and of course there's some feldspar left, but the alteration assemblage is getting more dominant and it's replacing part of the rock. And as you probably know, gypsum is not a very kind of hard mineral. It's not offering a lot of stability. You can scratch gypsum with your fingernail, and this kind of gives you already an indication that the alteration will not strengthen the rock, it will weaken the rock. And then we looked with the electron microscope into the smaller areas, and here's a VOC, and this VOC is filled with some material, and we did some element mapping. It basically scans the elemental distribution here, and here we did this for sodium. This is the plagioclases of the magmatic rock, and we can clearly see that they're different to the filling, the lining inside this VOC. And then we did this also for iron, and the iron intensity is different here. We have more iron in these. So these fluids that percolate through actually carry metals. It's very important in terms of how we think about how metals are concentrated. But what we also found is that they carry a lot of sulfur. So we have these sulfurous minerals, sulfates mainly, that are concentrated inside these VOCs here. So two things, we are replacing the main mineralogy, the original mineralogy, and we're depositing new things. So while this replacement makes the rock weaker, this kind of addition of extra material fills the cracks and VOCs and voids and vesicles, and therefore it actually makes the rock a little stronger again. So on first glance, it looks like that there's two competing processes when it comes to the mechanical strength. So we have looked at this then in more detail, and what we find here is that the porosity and the density actually correlate with the oxygen isotopes being an expression for how much fluid has passed through the rock and for the intensity of the alteration. Here we have the least intensely altered rocks. Here we have the most intensely altered rocks. So MERAPI fully altered is these samples here. MERAPI kind of rather fresh is these here. And we took some fresh reference samples from the deposits further down the hill. And this is the F samples, the fresh samples, they are here. So here we see a clear kind of change in the density and the porosity. And then we looked at the mechanical strength here. And we also see that the strength is decreased. So overall, while there may be competing processes, the weakening of the rock is the much stronger phenomenon. And the more porous the rock is, the more the weakness comes to bear as well. So if you have a vesicular rock and it gets altered, well, this is the kind of, indication that the rock is not going to hold a lot of weight. It's not a very stable situation. And if strength and porosity come together, we are more likely to have an unstable situation on the volcano. We termed this here the increased flank instability, the IFI. So the more we lose strength from alteration and the higher the porosity of the rock, the more likely the instability is favored. So this was the conclusion from the rock and mineral study. And this then is brought together in this diagram. This is a close-up shot from 2012 of this area where this fracture was then forming. And we see that things are unstable in that area. And then in 2015, this was getting stronger. We have more fissure and more alteration. And then we have the new dome growing over this. And this is the 2018 dome that has been growing over this. And it actually still collapses. There's still instability here. And it still falls down at exactly this weakness. And this led us to suggest that some of these collapses are actually happening as a result of hidden weaknesses. And this is the main gist of the paper and the main conclusion of the paper, that we actually have hidden mechanical weaknesses that are at times being buried into the volcanic structure, into the edifice by new dome growth, by new deposits. And if you're not aware of them, then you will not actually understand why there's collapses at these areas. And once you're aware that these structures exist, you can actually make some predictions. So the real consequence of that is that you have to look at your volcano very carefully and for a long time. You need to see where these weaknesses are located and how they become integrated into the volcano structure, how they get buried, for example. And once you know that, you have a better chance to actually make some sensible predictions of where instabilities may occur. So this is the main crux of the paper, that by doing these remote surveys, these drone surveys, and using this information structurally, as well as with the color analysis and understanding what these kind of processes mean from testing the rock record, we can actually improve things. So there's a long way to go. There's still a lot of work to be done, but this is a first step into saying that actually, if we look back to the things that happened and how the instability works, there is a signal for us. There's a way of trying to better understand, or there's an opportunity to better understand these instabilities at MERAPI Volcano and by analogy also at other volcanoes elsewhere. Thank you very much, and thanks for the team that has contributed to this article. I'm really happy that this is published now, and if you're interested, have a look yourself and you can read the details in the article. Obviously, there's also some supplementary material with the data, and it's open access, so everybody can download this. So I hope you enjoy that. All the very best and good luck.